Hello, I'm Swapnashri, and the topic I chosen for a natural language processing digital assignment is hidden Markov model. Now I'm going to talk about how this model is applied in NLP and the areas that plays a crucial role in modern technology. And the content I'm going to talk about HMM, that is the hidden Markov model, is introduction, the components of HMM, Viterbi algorithm, application, advantages and disadvantages, limitation, extension and alternatives, and conclusion. And it's a mathematical foundation and its Markov chain. And I'm going to talk about this. Next, introduction to HMM model, that is hidden Markov model. Hidden Markov model, this is an extension of a Markov process used to model phenomena where the states are hidden or latent, but they emit observations. For instance, in a speech recognition system like a speech to text converter, that state represents the actual words to predict, but they are not directly observable. That means that states are hidden. Rather, only you can observe the speech, that is audio signals corresponding to each word, and need to deduce the states using in the observation. HMM is a statistical model that represents a system with hidden states and that's transition from one state to another based on the probabilities. And this is used for sequence modeling, like where the underlying process is not directly observable, which are hidden, but output is observable. Similarly, in POS tagging, we observe the words in a sentence, but the POS tagging themselves are hidden. POS tagging tasks can be modeled as a hidden Markov model with the hidden states, which represents POS tagging that emit observation, that is words. That hidden states emit observations with a certain probability. Therefore, hidden Markov model has emission probabilities, which represents the probability that a particular state emits a given observation. And now, why we use this hidden Markov model in NLP? HMM is a particularly useful in NLP tasks like parts of speech tagging, speech recognition, and machine learning, and where text sequences can be. And also, NLP is a rapidly growing field that aims to teach machines and understand and interpret human language. One of the most important tool in NLP is hidden Markov model. And this hidden Markov model helps capture the probabilistic dependencies between words or linguistic instances in speech recognition, and the livelihood of one phenomena and other can be modeled with HMM transition probabilities. And the next topic is components of HMM. This involves states which are hidden states, and these represents the unobservable or hidden part of the model. For example, in POS tagging, the hidden states are the possible parts of the speech like noun, verb, etc. And the next one is observation, which are visible states which we can see. And these are the observable data we have, like in NLP. Observation could be words in a sentence, and the transition probabilities. This represents the probability of transitioning from a hidden state to another. Next one is emission probabilities. Emission probabilities means the probability of observing a specific word, like the specific word given in a certain state. For instance, the probability that the word run is observed when the state is a verb. Run is a verb, so it will be observed. Then the next one is initial state probabilities. The probability distribution of starting in a particular hidden state. These will be in the initial of the starting state only, it can be distributed. And the next one is graphical representation of HMM. The chain of states with transition probabilities between them, and the output observed, and the probabilities of each state. And the next one, the topic mathematical foundation, the joint probability. Here, the probability of an entire sequence of observed data can be calculated by multiplying the initial state probability and transition probabilities and emission probabilities. And the formula I will present in the PPT. So for this is the decoding inference problem. When we give a sequence of observation, what is most likely sequence of hidden states? For this question we are using Viterbi algorithm. I will explain this algorithm in detail. Now I'm going to explain about Viterbi algorithm. And this Viterbi algorithm is a dynamic programming algorithm used to find the most likely sequence of hidden state. It will find the hidden states. This is also called decoding. The steps we have to follow in this Viterbi algorithm are three steps, and these first one is initialization. In this initialization step, we will assign the probabilities to the initial states. We will assign the probabilities to each and every state. And the next one is recursion. By using previous states to calculate probabilities for the current, we will use previous states, and we can calculate the current state probabilities by using previous states. And the next one is termination. We can find the highest probability path and trace back. We will find this highest probability path and we will trace back this. And why we will use this in NLP. For example, in pure tagging, Viterbi algorithm would will give the most likely sequences of tags and the observed data. Now I am going to give some examples of HMM Markov model. And first example, we can take this parts of speech tagging example. Like we have to take a sentence, the cat sleeps. Okay, now in this the cat sleeps, the components might hidden explains in the components way. The hidden states, which the hidden states might be noun, verb, determiner. The observed sequences are the cat sleeps. Okay, now the transition probabilities might be the probability of transitioning from noun to verb and the probability of transitioning from determiner to noun. We have some probabilities like from noun to verb we take as 0.3 and determiner to noun as 0.7 as a random. Next one is in emission probabilities. The word the is more likely to be a determiner, as we know, and the cat is likely to be a noun and the sleep is more likely to be a verb. After all this, the initial state probabilities, the sentence starts with the determiner. So the probability might be 0.6 for noun, 0.2 and the verb 0.1. And the problem is we have to find the most likely sequence of previous tags for the sentence the cat sleeps. Using this Viterbi algorithm, we compute the probabilities for each possible sequence. Example start at the highest probability is that the is a determiner and move to cat. Cat, given the transition probabilities, the most likely tag for cat is noun, and the next one move to sleep. The given transition from noun, the most likely tag for sleep is verb. And final pivot tagging sequences, the is a determiner, cat is noun and sleep is verb. And next I'm going to talk about why this hidden Markov model matters. Because in NLP, the sequence of words or phenomena can be modeled using hidden Markov model to capture the relationship between these sequences. Like in parts of speech tagging or speech recognition benefit from HMM because they model both the dependencies between states and livelihood of observing specific outputs, making them a robust tool for sequence analysis. Now I'm going to talk about the applications. First one is parts of speech, POS. In this hidden Markov model, it is used to predict the most likely sequences of POS tags for a sentence based on the transition probabilities. Like we can take a sentence, the cat sleeps. So here the POS tagging might be the is a determiner or pronoun, and the cat is a noun and sleep is a verb. Like that we can give the tags for each sentence. Example, the livelihood, the verb follows a noun and emission probabilities. Example, the livelihood, the word run is a verb. And next one is speech recognition. In this speech recognition, hidden Markov model is used to model the sequence of each sounds and the corresponding text transcriptions with hidden states being phenomena and observed data being the acoustic signals. And the next one is named entity recognition, which is also called NER. In this named entity recognition, this hidden Markov model can help to classify words into categories such as person, organization, or location by modeling transition between categories and the livelihood of words appearing in those categories. And now I'm going to talk about advantages of hidden Markov model and disadvantages of hidden Markov model. And the first one is effective for sequential data, like in HMM, which is specially designed to handle a sequential data, making it clear, ideal for tasks like POS tagging and speech recognition. And the next one is probabilistic framework. This provides a robust probabilistic approach to modeling uncertainty and noise and making it effective in real world applications like speech or handwritten recognition. And it is well established and interpretable. Where hidden Markov model has been around for decades, it is well understood and is relatively easy to interpret, easily compared to complex deep learning models. And it is also an efficient decoding algorithms. By using these Viterbi algorithms, which allows for efficient decoding of most likely sequence of hidden states, making HMM computationally feasible for many tasks. And the next advantage is it is easy to train with small data sets. Example, HMM can perform well even with the smaller label data sets, making it useful in situations where large scale data is not available. Now we are going to talk about disadvantages. First disadvantage might be it is limited to first order dependencies, where hidden Markov model only considered the current state and the previous state. It ignores the previous states, so that longer range dependencies might be important in languages. And the next one is simplistic assumption. This assumes that transition between states follow the Markov property, which only considers the current state and ignores the other states. And the next one, it struggles with the large vocabulary size. Like in HMM, it becomes computationally expensive when dealing with large vocabularies and complex language models, especially with many possible hidden states, which is more expensive. And the next one is it is very poor at handling ambiguity. When multiple words or phrases share similar probabilities, it may struggle to choose the correct sequence due to its limited feature set. So it is poor at handling ambiguity. And next one is outperformed by model these HMM are largely being replaced by more advanced models like conditional random fields, deep learning approaches, which better handle complex dependencies. And the limitations of hidden Markov model. This hidden Markov model assumes that the probability of event occurring in a certain state is fixed, and which may not always be the case in real world data. And additionally, this will not be well suited for modeling long term dependencies in language, as it only considers the immediate past. And these are the alternative models to HMM in NLP, which includes a recurrent neural network model and transfer model like BERT and GPT. These models have shown promising results in a variety of NLP tasks, but they also have their own limitations and challenges. And the next limitation is assumption of Markov property. And these HMM assumes that the probability of transitioning to the next state depends only on the current state but not the previous states, which may not always be valid in complex NLP tasks. Next limitation is handling long dependencies. It struggles with long range dependencies because due to its memoryless nature, it only considers the current state for transition. It might be a disadvantage, like it can't use for the long range dependencies because of the only current state transition. And the next limitation is scalability. In this scalability with large vocabularies and many possible hidden states, a hidden Markov model can become computationally expensive in many cases due to large vocabularies and large range dependencies and more possible hidden states. This hidden Markov model will become computationally expensive. And so, due to the limitations or disadvantages, we can also use the extensions and alternatives for hidden Markov model. First one is conditional random field CRFs, which is also called CRFs, conditional random fields. Conditional random fields are often used as an alternative to hidden Markov model for a sequence labeling task like parts of speech tagging, as they don't assume independence between observer variables and can model long range dependencies better. So this might be a good alternative or a better option, better than hidden Markov model, because which it don't assumes the independence between observer variable and can model long range dependencies also. And the next alternative is deep learning approach. In this deep learning approach, recurrent neural network, which is called RNN, and long short term memory LSTM, these networks now are more commonly used for tasks like parts of speech tagging, speech recognition, and machine translation, as they can capture more complex pattern in sequential data. So these conditional random fields and deep learning approach might be a better option than the hidden Markov model, because these provides long range dependencies and I don't assume the independence between the observed variables, and also be a better option for POS tagging, speech recognition, and machine translation, because they can capture complex pattern in sequential data. And the conclusion, and I conclude that these hidden Markov model are valuable in natural language processing, because they can model and predict hidden patterns in language data, making them suitable for tasks involving sequences of text or speech. Their ability to capture dependencies between words and handle hidden structure and work within a probabilistic framework and makes them foundational for earlier and even more current NLP applications. And the conclusion and key takeaways may also include, here we summarized how this hidden Markov model is used to model sequential data in NLP, and with importance tasks like POS tagging, speech recognition, and how despite its limitation, and it's laid the groundwork for more advanced models like CRF and RNN, and also these alternatives, and reinforce that while HMM may not be as widely used today, but understanding it is crucial for grasping the evaluation of sequence modeling in NLP. And this structure ensures you cover the essential components of HMM while staying and now I conclude that I have I spoke about in hidden Markov model introduction to what is the hidden Markov model, why we have to use this hidden Markov model in NLP, and the components like states, observation, transition probabilities, emission probabilities, initial state probabilities, graphical representation, and I spoke about Viterbi algorithm and the steps involved for initialization, recursion, and termination, and the applications, parts of speech recognition, named entity recognition, and also advantages and disadvantages of HMM model, and the limitations like assumption of Markov property, handling DOM dependencies, scalability, and extension and alternatives like conditional random fields, deep learning approaches like recurrent neural networks, long short-term memory, and these all I conclude these and I have spoke about all these introduction, components, Viterbi algorithm, applications, advantages and disadvantages, limitations, extension and alternatives, conclusion, and finally what is HMM means, which represents a system with hidden states where the system transitions from one state to another based on the probabilities, and also used for sequence modeling where the underlying process is not directly observable, which is hidden, but output is observable.